Welcome to the Explainer. So today we're stepping into a clinic, but, well, not the kind with human patients. Instead, I want you to imagine for a second that you're an industrial doctor, and your patient, it's a massive solid steel pipeline. Or maybe an aircraft engine component, or even a critical structural weld. Just like a medical doctor uses an ultrasound to safely look inside the human body, we use industrial ultrasonic testing, or UT, to peer deep inside solid metals and materials. And in this explainer, we're going to uncover exactly how this invisible diagnostic magic actually works.
It all starts with one fundamental question, right? How do you look for microscopic, hidden cracks inside a chunk of solid steel without breaking it apart? I mean, you can't exactly just pry it open to check if it's healthy. The secret lies in the incredible power of high-frequency sound waves. By sending very specific sound waves right into a material and just listening carefully to how they echo back to us, we can paint a remarkably accurate picture of the invisible flaws hiding just beneath the surface.
Okay, let's dive into our syllabus for today. We'll start with the magic of sound, then we'll learn how to speak the wave language. Next up, the tools of the trade, followed by the pulse echo method, contact versus immersion testing, and finally, we'll wrap up by looking at the future with TFM. Let's get right into it.
Section 1. The magic of sound. We're going to explore the actual physics of ultrasound.
Now, when we talk about ultrasonic testing, there is one crucial number you really need to remember, and that's 15, specifically up to 15 megahertz. In UT, we're typically firing incredibly short ultrasonic pulse waves, and their center frequencies range from 0.1 all the way to 15 megahertz. Sometimes, highly specialized tests even push that limit to an astonishing 50 megahertz. Now, just to put that into perspective for you, human hearing completely taps out around 20 kilohertz. So we are talking about literally millions of cycles per second here. These sound waves are so incredibly fast and energetic that they exist in a realm totally undetectable to our human ears, but they are absolutely perfectly tuned for slicing right through solid steel.
Moving on to Section 2, speaking the wave language. Let's see how sound actually travels through solid matter.
The absolute most important term you're going to learn here is acoustic impedance. Think of this as a material's very own unique sonic fingerprint. By definition, it's just the product of a material's density and the velocity of sound traveling through that specific material. And it is absolutely crucial because this impedance dictates exactly how sound is going to behave, especially when it hits a boundary, like hitting a totally new material. That could be a crack filled with air or even a pool of water.
So the big takeaway here is this specific formula, Z equals rho times V. Z is our acoustic impedance, rho is the density, and V is the sound velocity. This single equation is the scientific foundation that explains why sound travels so wildly differently through a pool of water compared to a block of steel, or just the ambient air around us. Because air has a completely different density and sound velocity compared to steel, the acoustic impedance mismatch between those two is, well, it's absolutely massive.
Let's actually look at what this wave travel looks like on a microscopic level. If you check out the grid of black dots on the screen, those represent particles. You see, acoustics isn't just magic. It's quite literally about forcing these particles into vibrational motion around their equilibrium positions. As the wave travels from left to right, which you can see indicated by that top blue arrow, the individual particles aren't actually migrating all the way across the material. Nope, they're just vibrating back and forth right in place, transferring that kinetic energy directly to their next-door neighbor. And this brings us to a brilliant illustration of the two main modes of vibration we use in testing, longitudinal and shear waves. Take a look at that top diagram showing longitudinal waves. Imagine you've set up a long line of dominoes, and you push that very first one forward. That compression moves parallel to the direction of the wave, right? That is a longitudinal wave. Now, contrast that with the bottom diagram for the shear wave. Imagine you're at a massive sports stadium, and the crowd starts doing the wave. The wave itself travels horizontally all the way around the stadium, but the people, our particles in this analogy, are just standing up and sitting down, which is completely perpendicular to the wave's actual direction. We use both of these very distinct wave types to interrogate materials in totally different ways.
But here's the thing. Sound doesn't always just travel in a perfectly straight line. And that brings us to Snell's law, which explains refraction. When a sound wave traveling through one material hits an interface with a second material that has a different acoustic velocity, the wave actually bends and changes direction. It's exactly like if you were shining a flashlight into a swimming pool at night and you watch the beam of light visually bend right in the water. By calculating these specific angles, inspectors know exactly where their sound beam is pointing, even inside really complex shapes.
All right, Section 3, Tools of the Trade. Let's talk about generating and transmitting this sound on a real job site.
So a typical UT setup is going to rely on 4 main components. First, you've got your pulsar/receiver, which is basically the electronic brain producing the high-voltage pulses. Then you have the display device, so you can actually see the data. But I want you to pay special attention to the transducer. Hidden inside that transducer is a tiny, highly specialized piece of polarized material called a piezoelectric crystal. When you zap this crystal with an electrical pulse, it physically vibrates, which generates our high-frequency sound waves. And the really cool part? It works in reverse too. When an echoing sound wave bounces back and hits the crystal, it converts that mechanical vibration back into an electrical signal that we can actually read on our screen. It really is the absolute heart of the whole operation.
There is one catch, though. We can't just press our dry transducer against a dry piece of steel. We absolutely need our fourth tool, the couplant. Remember when we talked about acoustic impedance earlier? Well, sound absolutely hates trying to jump the physical gap from a solid transducer through a tiny layer of air and into solid steel. The impedance mismatch is just so ridiculously high that nearly all of your sound energy will literally bounce right back off the surface. So to fix this, we use a liquid couplant, something like oil, glycerin, or just water, to completely displace that pesky air gap. It acts as a perfect acoustic bridge, allowing all that sound energy to safely cross over into the material we're testing.
Moving on to Section 4, the pulse echo method. This is how we actually listen for the hidden flaws.
To understand why the pulse echo method is so universally popular, we really need to contrast it with something called the through transmission technique. Now, through transmission requires 2 totally separate probes placed on opposite sides of a part. One is transmitting the sound and the other is receiving it. You're basically measuring how much energy gets lost as it crosses through the material. But pulse echo, it only requires one-sided access. It is literally just like standing at the very edge of the Grand Canyon and shouting into it. You send out a very short pulse of sound, and then you just wait and listen for the echo. If the sound travels all the way through and hits the back wall of the material, you get a late echo. But if there's a hidden crack lurking halfway through, the sound is going to hit that crack and bounce back early. By measuring that super precise travel time, we can figure out exactly how deep the flaw is.
Section 5. Contact versus immersion testing. Let's look at the different environments where we create that perfect bridge.
Now let's look at an immersion testing setup, like the diagram we have right here. Let's visually follow the signal from top to bottom. Way up at the top, you can see the electrical cable leading down into the transducer probe itself. But notice something super important. The probe isn't actually touching the material at all. Instead, it's fully submerged inside a tank completely filled with water. And the gray material we're inspecting is just sitting down there at the very bottom. In this specific setup, that entire column of water between the probe and the part is acting as one giant, continuous liquid couplant bridge.
Now, you're probably wondering, why on earth would we go through all the hassle of completely submerging these parts? Well, immersion testing offers some really incredible advantages. First off, it lets us use significantly higher frequencies. We're talking sometimes 25 megahertz or even more. And that dramatically increases our sensitivity, allowing us to catch incredibly tiny, microscopic defects. Furthermore, the water provides a perfectly even acoustical coupling. Think about it. If a human technician is pressing a probe against a piece of metal by hand, their physical pressure is naturally going to vary, which actually alters the signal. Using a water tank removes that human variable completely. It ensures perfectly consistent pressure, making it highly adaptable for automated super high-speed robotic inspections, all without putting any friction or wear and tear on the physical probe itself. It's a total game changer.
Finally, Section 6, the future with TFM. Let's see how advanced algorithmic imaging is changing the game.
All right, this brings us to some seriously cutting-edge tech. Full matrix capture, or FMC, and the total focusing method, which we call TFM. So, instead of using just a single crystal, I want you to imagine a probe packed with an entire array of dozens of tiny crystals. Here is the step-by-step of how this actually works. Step 1. The system activates and physically fires each individual element one by one in a sequence. Step 2. It records the returning echoes from every single receiving element and dumps all that data into a massive raw matrix. Amazingly, it doesn't even need to know the shape of the part yet. Then, Step 3. This is where the actual magic happens. The total focusing method algorithm takes that massive grid of raw data and it synthetically focuses the image at every single point in the region. Unlike the older methods that force you to focus at one specific depth, TFM uses sheer computational power to create these perfectly focused, comprehensive 3D-like images of defects everywhere in the viewing area, all simultaneously.
So from sending basic high-frequency pulses to crunching massive matrices of synthetically focused data, our industrial doctor has certainly come an incredibly long way. The ability to guarantee the absolute safety of our massive pipelines, commercial aircraft, and critical infrastructure relies incredibly heavily on these exact principles of acoustics. Which really leaves us with a totally fascinating thought. As our computational power continues to explode and our algorithms get even smarter, what microscopic, invisible flaws will ultrasound reveal next? Thank you so much for exploring the magic of sound with me today in this explainer. Keep your ears and your transducers open for what's next.